lecture also. So that was this particular example from simple harmonic motion, where you had two blocks. You are applying attached by a spring, which are initially at rest. Now I had asked you to solve yourself using a simple case where the two blocks are of equal mass, but I will solve the more general case here where the masses are M1 and M2. Initially, if the spring is having zero extension and both the blocks are at rest, and we set the system off by applying a constant horizontal force. At time t equal to 0, this starts this way. So then we can see that at a general time t, there will be a certain amount of extension. This will have some acceleration, this will have some acceleration. But more importantly, the center of mass of the system will have some acceleration, because the net external force acting on it is F. So the acceleration of the center of mass will be F upon M1 plus M2, which will be constant, or a uniform acceleration. So we want to show that M1 and M2 perform SHM in the center of mass frame. Okay. Find the time period. Amplitudes for the individual blocks. Okay. And also find the maximum extension for the spring. So all these things we want to do. Okay. So this will be a case similar to the previous ones that we have done. The difference is that in the previous two cases, the center of mass was either at rest or moving at uniform velocity. So in both cases, the FBDs that we were making of the blocks were in inertial frame. Even if it was a moving frame, it was an inertial moving frame. Now it will be the case of making FBD of M1 and M2 in the center of mass frame, which will become a non-inertial frame because it is accelerated. So we'll have to take pseudo force into account. And again, the procedure will be the same, that from the dynamics of each block in the center of mass frame, we'll be able to show that they are performing SHM. And from the initial conditions and all that, we'll be able to find the amplitude and phase constant. Okay, so just try this out from that context. Okay, so what we'll do, the first step we'll do here is make FPDs for the blocks M1 and M2 in the center of mass frame. Okay, and solve the dynamics to, you can say, derive equation of SHM. And then the second step will be that use the initial conditions, initial state or conditions, whatever, to find amplitudes and phase constants. So just take a minute to try out the first part, the dynamics part, we will discuss. Okay, so I'll go ahead and make the free body diagrams. Okay. So first of all, we are in the center of mass frame, which now becomes a non-inertial frame, which is traveling with that acceleration that we have written now. So let's say initially when the system started off, this is where the blocks were. I think this one was M2, right? And this one was M1. So this is at t equal to 0. Okay. So at t equal to 0, there's no spring force on either one of them. So on this, there is F and there is pseudo force. And on this, there is pseudo force. So the initial acceleration of this guy is like this. The initial acceleration of this guy is like this. And write this as initial accelerations with respect to center of mass. So this is this one's acceleration. Okay. Now at some time t, remember x of the spring was 0 at t equal to 0. At some time t, the spring has got stretched by x, let's say, because this has got displaced by x1 and this has got displaced by x2. So at some time t, x is equal to x1 plus x2, the spring. So in that same center of mass frame, we have the same pseudo force, external force. But in addition to that, now you have the spring forces. The same magnitude of spring force on each. So this is where all this will now come in, that x is equal to x1 plus x2 and m1 x1 is equal to m2 x2, because in center of mass frame, displacement of center of mass is 0. From that is coming. Okay. So we get this individual equations that x1 is m2 upon m1 plus m2 x and x2 is equal to m1 upon m1 plus m2 x. So this is like a constraint relation set, this and this. So when we incorporate this in the FBD equation, you'll see we get the SHM equation. So for this block, we have F minus M2 ACM minus KX is equal to MA. So we'll have that kind of term, M1 by M2 minus KX is equal to minus M2 D2 X2 by DT square. So I got this. Now I'll need to incorporate this over here so that I get the SHM equation. Okay. Similarly, for this one, I have M1 ACM minus KX is equal to M1 A1 . One less term in here. So just absorb this information and now substitute x1, I mean x in both these equations in terms of x1 and x2. And you'll see you will get the SHM equation with that same formula of omega squared. Omega square will become k divided by reduced mass. But now your SHM equation will be of this type, that d2x by dt square is equal to minus omega square x plus some constant. So x will become a sine omega t plus phi plus c by omega square. We get this secondary form of SHM with the displaced equilibrium point.
So,
Yes.
so but the acceleration of center of mass was equal to a1. So in the equation of m1,
Which acceleration was equal to a1? Acha, in the initial one, na? Initial a10. Yeah, that's correct. No? Because actually in the ground frame, if you see, na, initially a1 is at rest. Rather, initially m1 is at rest. So obviously, the center of mass, whatever acceleration it has, in the center of mass frame, it has that much negative acceleration. You understanding the point, no?
yes.
Like suppose when you look in the ground frame, what you're observing is that the center of mass is setting off with an acceleration of whatever, let's say ACM is equal to 2 meters per second square. So next, when you get into the center of mass frame, and this one is at rest, okay, you see that this one has a negative acceleration of 2 meters per second square in the center of mass frame.
Okay.
But again, you'll see the other thing is that the other block has a different acceleration, and again you'll see that in this frame the center of mass is at rest. Okay, so m1 is a1 will always be equal to m2 a2 in the center of mass frame. So remember here everything is with respect to the center of mass. So this will apply for even this initial value as well as the general value. Okay, so incorporating these two equations here, now we'll say that this equation becomes that d2x1 by dt square will become minus omega square x1 wait, we have to write this as plus only over here, my mistake. Okay? This will be plus only because I've taken the direction of the acceleration in the diagram. You can see the direction of acceleration a1 is in the direction of x1 and the direction of a2 is in the direction of x2. So these are with the plus signs. Okay. So anyway, so this will become minus plus okay, where omega square is equal to because the inverse of this relation is that reduced mass. Okay. Like this. And this equation here, this will become similarly I've just mixed up the variables just a moment. These should all be x2. So our x1 as a function of time will become like a1 into 1 minus cos omega t, and x2 as a function of time will become like a2 into 1 minus cos omega t. So x as a function of time is x1 plus x2. So X's maximum value will be 2 times A1 plus A2. So this relation. This relation. So there's another way of understanding this maximum extension also. We'll discuss about that. So I'll just minimize it a bit from here. Okay, so for example, if we had a numerical situation where let's say M1 is 6 kgs, M2 is 3 kgs, okay, and the spring constant was, let us say, 2 newtons per centimeters, and the external force we applied was, let's say, 12 newtons. Okay. So we would see that first of all, our reduced mass would come out to be 2 kilograms. So our omega square for the SHM would have come out to be K divided by reduced mass. So omega would be 10 radians per second. Now what we'd also see is that this particular case, A1 whereas C1 would have been F divided by M1 plus M2. So let's make this an easier number to handle. Let me change the force to 18 newtons. Okay. So this would become 2 meters per second square. So A1 this one's amplitude would have been 2 centimeters. Now it's very easy to understand that the other one's amplitude should be such that M1 A1 should be equal to M2 A2. So you see that A2, I've taken M1 and M2 as 6 and 3. So A2 should be double. It should be 4 centimeters. But let's check out the value of A2 this way also. So A2 from here is C2 by omega square, and C2 would be M1 by M2 times F upon M1 plus M2. So C2 would be 4 meters per second square. So the second one's amplitude would be 4 centimeters. And therefore, we would see that the maximum, so x1 as a function of time would be A1 1 minus cos omega t, x2 as a function of time. So x as a function of time would be like this, where 6 centimeters. So the maximum extension would be 12 centimeters. So this would be a numerical example of this particular situation. So I'll just discuss to you how this happens dynamically speaking also. This all we have got from SHM. Okay, now very quickly, I'll take you through the steps if we were to show this amplitude business and all dynamically speaking. So, you just relate this like this, that that if you have a system like this, which is having x equal to 0 initially, u equal to 0. Okay. Then that, it will have a range of motion where at the equilibrium position, x will be f by m, and therefore the maximum amplitude will be double of that, no? Because I mean the maximum displacement will be double of that, because and here at the equilibrium position v will be maximum. So that your amplitude will be f by m, and your maximum extension will be 2 times amplitude, or 2f by m, and in general your x will be a into 1 minus cos omega t. It is something that you know from work energy also before. So when you translate this to this kind of system now, so in the center of mass frame, you're seeing that F pseudo force, okay, is giving this an initial acceleration, and just pseudo force is giving this an initial acceleration. This is your extreme position. Okay, so like this was your extreme position. This was your extreme position, and in between here, this is your mean position. On either side, there's amplitude. So like that, this is your mean position. So what is your sorry, this is your extreme position. So what is your mean position? The mean position will be the value at which this one's acceleration becomes 0. This one's acceleration becomes 0. So at the mean position on this block, M1 ACM has to be balanced with Kx. On this block, F M2 ACM has to be balanced by Kx. So at mean position, you have, and so either of these you'll solve, and you'll see that your x will come out to be this kind of thing. It will come out to be x. So this is basically such that the maximum extension of the spring will be twice of that. And this will also be such that this is one amplitude for this one, and this is one amplitude for this one. Because this is the mean position, this is extreme. This is the mean position, this is extreme. Okay. And therefore the other extreme will be at this side. This is when your V will become 0. And here it is L plus X maximum. So this X maximum is twice of A1 plus A2. Whereas here, this is L plus X, where at the mean position, X's value is A1 plus A2. This is the starting position where this was L naturally. Okay. So you can see that X max is this. Okay. Also, this is A1 plus A2. And you have M1 A1 is equal to M2 A2. So that's how you will understand that A1 will become and A2 will be X. So this is your amplitude of the spring. So might seem a little bit complicated initially, but just go over this couple of times and also repeat this analysis with a numerical example I've given you, that 3 kg, 6 kg case and all that. So you will see you'll get used to this and you can solve for amplitude and all this pretty fast. But of course, remember this is like a lengthy question at JEE Advanced level. So if at all it's for a paragraph question, which is testing you for center of mass along with SHM concepts. So this example. So this is a bit of advanced work with simple harmonic motion, but also incorporating a lot of ideas from center of mass. More of it actually to do with center of mass, motion of center of mass, and FBDs in center of mass frame, those kind of analysis. Okay, so hope this is clear, people. So with this, now we move on to the next section of physics, which is actually in many sense a continuation of COVID. We have to also discuss about damped oscillation. Yeah. Before we get into waves, we have to discuss about damped oscillations, which is specifically for yes, Nikita, thanks for reminding me. This is specifically for JEE Mains only. It is not in JEE Advanced syllabus. JEE Mains and boards only. Okay. So damped oscillation is a situation where on any body, if this is the mean position, now at a position x equal to x, there is a restorative force, which is like this. But along with that, if the body is moving in this direction, there is also a damping force. Okay. On the other hand, if the body is at here, then the restorative force is still like this. But along with that, now suppose it's moving in this direction, then the damping force will be in this direction. Suppose in this diagram also, it's moving in this direction towards the mean position, then the damping force will be opposite to that. Okay. So if a body experiences a combination of two forces, restorative force proportionate to displacement from mean position. it experiences minus kx type of force. And secondly, along with that, it experiences a drag or damping force given by minus cv. So c is a constant and v is the instantaneous velocity. So the net force on the body becomes a combination of m d2x by dt square this kind of situation. Then this is the dynamics of a damped SHM. So just note down this basic equation first, then we'll discuss about the solution of it and x as a function of time. It is called a damped harmonic oscillator actually. This is the equation of a damped harmonic oscillator. So the physical situation would be something like this. We have a spring mass system on a smooth surface, but inside a tank. So this is a smooth surface, but inside a tank which has some viscous fluid. So then at any instant when the body is, let's say, moving like this, apart from the fact that spring force will act on it, there will also be the damping force. With the opposite direction. So that is the physical example of it. Or we can write this equation like this, that m d2x by dt square plus kx plus c into dx by dt is 0. So now what happens, unfortunately, at our level is that this differential equation is a bit advanced for us to solve with our level of calculus. So we will not be able to solve it the way we had solved the harmonic oscillator equation, that is d2x by dt square is minus omega square x. We had solved that differential equation to prove that x is harmonic in time. So that kind of proof we will not be able to do here, but we will do some analysis based on this. Okay, so in the analysis, the first term that we'll define for this kind of an equation is something called the damping coefficient. Okay. So two terms we'll define. Of course, we have seen one before, the damping force. It is minus CV or minus c dx by dt square. Sorry, dx by dt. And the second thing we'll define is the damping coefficient. And we'll see that the damping coefficient plays an important role in the analysis. So typically we denote the damping coefficient by the formula, I mean by the symbol gamma, and it is given by the formula c by 2m. Because always remember it is not c by m, but it is c by 2m. So this damping coefficient plays an important role. So it's kind of like this, that it's proportional to c, because stronger the damping, the larger should be c. But also this damping coefficient is inversely proportional to mass, because more the mass, more the inertia. So less effective the damping. Okay, so that's one way to remember that it's proportional to c by m, but that factor of half, it is a pure numerical constant, and there is no way to justify it at the moment why it's that. It actually comes from a more lengthy approach of deriving the solution of this equation, which we cannot get to at our syllabus level. It's probably one of the reasons why it's not there in JEE Advanced syllabus. It's only there in JEE Mains syllabus. Anyhow, so now we'll see that this damping coefficient plays an important role, because the value of the damping coefficient, okay, determines an important thing over here. Okay. So we will see that the equation of the harmonic damped oscillator, that is the dynamical equation, it results in a solution. So this equation solution, this one solution is that x will be this type of a term. It will be like a multiplication of two terms, an exponential decay and a harmonic term. So this is the damped harmonic oscillation equation. X as a function of time. So you can think of it like E into e raised power minus gamma t. This is a decaying amplitude. It's a time decaying amplitude. And the sine omega 1 t plus phi, this is an oscillating term. It's a harmonic term. The time period like this. Okay, now in this, obviously gamma is the damping coefficient. We have already seen that. So it's given by the formula C by 2m, remember? Okay. But what about this omega 1? So this omega 1 is an interesting term. This omega 1 is actually related to the natural harmonic frequency in this way, that it is square root of omega square minus gamma square, where omega square is basically k by m. So the idea is in this equation, you can see something very nicely. If C is 0, that is damping force is absent, okay, then it nicely subjects itself to this. So it incorporates that gamma will become 0. So this term will, sorry, e raised by minus gamma t term will become 0. So the amplitude will be constant. And also omega 1 will become omega. So the time period will be 2 pi under root m by k. But if gamma not equal to 0, so then C is not equal to 0. It means that the amplitude decays with time. And now there is interesting cases. Okay, omega 1 might be a real number, it might be 0, or omega 1 might also become imaginary. That leads to 3 different cases. This is the case where gamma is less than omega, or C by 2m is less than k by m. This is the case where gamma is equal to omega, or C by 2m is equal to square root of k by m. And this is the case where gamma is greater than omega. So C by 2m becomes greater than root k by m. Now C square is less than 4mk. C square is equal to 4mk. And C square is greater than 4. So for gamma not equal to 0, there are these 3 separate cases discussed. 3 separate cases that can occur, which we'll discuss about. But of course, if C is 0, there is no damping, so it's a regular SHM. So this is then a regular SHM where our equation is becoming Okay. Now we'll see that each of these cases has a special significance. Okay. So this first case, so we are talking about this general. So let me list out the important things again. Okay. So the general equation is again that m d2x by dt square, okay, plus kx plus c dx by dt is equal to 0. So this is giving us a general equation that x is this kind of exponentially decaying kind of amplitude into a harmonic term sine omega t plus phi. And only here gamma is c by 2m damping coefficient. So actually everything we need to know I'm just listing out over here. Okay. And omega 1 is square root of omega square minus gamma square. So now we'll see that case 1, which is called the underdamped case. So underdamped case, this is what is happening. Your omega 1 is real, c square is less than 4mk. So omega 1 is a real number. So in this case, the oscillation actually looks like this. It looks like what we expect it to be, a harmonic alternating term, x as a function of time, but with a decaying amplitude. So if we use this as a sort of e raised power minus gamma t, and this as minus of e raised power minus gamma t kind of term. So you'll see this is what it looks like, where this cyclical time between any two crests or any two troughs will be equal to 2 pi by omega. And the amplitude at any instant will be equal to that. So this is the first case, underdamped case. As the name suggests, this is the case where the restorative force dominates. Over damping. It still makes it possible for it to go back and forth, even though it does not perpetually oscillate, because eventually the amplitude decays to 0. So this is called the underdamped case. Next, we will see something called the overdamped case, or the critically damped case. Right. Now the next case will be what we call the critically damped case. Where c square is equal to 4 mk. So omega 1 becomes 0. So then you can see there is no harmonic term, okay, because that omega term inside that omega 1 t term inside the cos function or the sine function, the harmonic term, it does not exist. So critically damped case will look like this. Without alternating, without oscillating, it will just decay to zero in some finite amount of time only. And the third and final case also is very similar to this, so we can include it here. The overdamped case, where basically the damping dominates. So now this is something that is going to be mathematically hard for us to understand why it is this way, because we're not getting into the solution of that differential equation and all that. But this will also be like the critically damped case, but this will just be like, it will be asymptotically approaching zero as t tends to infinity. So there's hardly much difference between the critically damped and the overdamped situation, because even though the overdamped graph seems to suggest that it goes on for infinity, but remember these kind of exponential decay graphs, for practical purposes, they approach zero very soon. Okay, because this value of x becomes so small that it becomes negligible after a bit of time. Like you might have seen in the RC circuits, I don't know if you've done in capacitors yet, discharging of a capacitor, charging of a capacitor, those kind of circuits. Or we have seen in the case of exponential graphs in the case of viscosity earlier. In fact, this is basically something like that only. Along with viscous force, there's also a restorative force. That's the only difference. Because earlier we've seen only viscous force in action, or combination of viscous force, weight, and buoyancy and things like that. So it's just these factual things that you have to keep in mind, because this is a JEE mains level topic. So you have to just remember these critical things. The whatever you have to remember actually is right here. The general equation of a damped harmonic oscillator. Okay. In that, the definition of damping coefficient, okay, and x as a function of time, where omega 1's relationship is like this. Of course, you remember omega square is k by m. So if you put c as 0, then it reduces to a regular SHM, a sine omega t plus phi. But otherwise, it is this kind of damped oscillation, which can have these three different cases. Okay. The first one is the one that we intuitively expect, that it's oscillating but with decaying amplitude. But that is the case where it's underdamped. So the restorative force still dominates to a certain extent, and the damping coefficient or the damping force just has the role of gradually decaying the amplitude without really changing the behavior of the to and fro motion, apart from the fact that the amplitude reduces. Whereas in the critically damped or overdamped case, it's actually the other way around. The decaying force or the damping force is dominating in such a way that basically it doesn't allow it to go to and fro. The motion dies down before that happens. It has a very strong dominant kind of effect. Right, so that's all about damped oscillations. Now, one more thing is going to be a combination of SHMs, which again is also going to come up in waves when we discuss that chapter next. Combinations, or we can say superposition of SHMs. So for example, if we have one SHM given by this and another SHM given by this, and the resultant motion along the x-axis is due to the superposition of these two. So the resultant oscillation along x-axis is the superposition of the above. Then there's a particular way of solving this, and that shows that the superposition results in this kind of a term, where the net amplitude is given by this kind of formula. So we'll do a derivation of this also very soon, but just want to make you familiar with the formula first. So it's very similar to the vector formula actually, even though it's not a vector addition. But mind you, what we are doing here is that the two SHMs that are being superimposed. Actually, we have done this in the last lecture, is it?
Yes.
Okay. Let me just quickly check the notes.
Last or way before that?
Yes.
Then it must be the last to last lecture, no? The one before that.
Yes.
Yes.
Okay. Fine. So then we can actually move ahead to waves. Okay, so this is already done. So we are done with SHM now. Okay, so it's fine. So you must have done this before your test, before the last major test.
Yes, sir.
Okay. All right. So okay, we have some time to go, so we can take a nice introduction into the next chapter, which is wave mechanics. So the next section of physics for us is wave mechanics. Okay. So first of all, we'll try to understand a sort of broad meaning without getting into a technical definition. We'll get into a sort of a meaning of the term wave, or wave motion, okay, or any wave phenomena. How do we classify a given situation or a given physical phenomena as a wave phenomena? Okay. Can you give me some examples of waves, examples of wave phenomena from your everyday life?
Sunlight.
Sorry, come again.
Sunlight.
Yeah. So propagation of light, including sunlight, is a wave phenomena. Very good. But interestingly, that is what we call an electromagnetic wave. But yes, it comes under wave phenomena. Can you give me some examples of waves in sort of physical domain as opposed to electromagnetic domain? Ocean waves.
Sound.
Yes, very good. Sound, propagation of sound. Very good, Smita. Okay. Then anything little bit more abstract you can think of? Obviously, light we have talked about just now. Electromagnetic waves. Light, radio waves, X-rays, microwaves. These are all in the domain of electromagnetic waves. Ripple formation in water, part of ocean waves. Okay. Any of you seen Mexican wave in a crowd?
Yes.
Yes.
Sir.
In crowd, a stadium or something like that. That's also a wave phenomena. Okay. Now, how do we actually, what is the common feature in all of these things? Like they're quite different. Ocean waves on its own is quite different to sound waves or Mexican wave in a crowd. Or I'll give you an even more abstract example. You take the whole situation of information via internet. Information transfer via internet, whether it is through email or video conferencing or anything like that. Okay, if anything is happening, any information is passed from one point to another via an internet, I'll definitely say it is a wave phenomenon. Okay, whereas as opposed to this, if I say there is sending a letter to somebody, okay, this is an example of a non-wave phenomenon. Or if I talk about free fall, of a body, if I talk about orbital motion of a planet, is all example of non-wave phenomena. Yes, pandemic wave, unfortunately, a very sad truth in our lives, but that's also an example of wave phenomena. So what you'll see is different about this with respect to this is that any wave phenomena involves propagation of energy or information. You can call it a signal or whatever also if it's in the electrical domain. Okay. Without physical propagation of particles. Okay. In mechanical waves, particles of the medium do move, but particles of the medium oscillate about a fixed mean position. And in the process, energy propagates. So you can see that, for example, if you have sent information from one point to another via letter, you've actually taken a rigid body in which the information is encoded, because the piece of paper is, you might not call it a rigid body, but whatever, it has mass, it's matter, it's substance, in which you've encoded the information by writing. So the ink has created a chemical reaction, creating something that is visible, whatever, blah blah blah. But all that matter is actually moved from point A to point B, and through that the information is transferred. But if you look at the example of email communication or communication by sound, what I'm saying is reaching somebody else who is at a proximity to me. So it is not like I have set out some particles from my vocal cords and those particles are transported all the way from my vocal cords to your ears, and that is causing the information to get transferred. Yes, I have caused some motion of particles. My vocal cords vibrating is causing vibration of air molecules in my thoracic column, and that is causing sound waves to propagate. And those sound waves are causing ultimately your eardrum to vibrate, and that's converted into a neural impulse and all that. But at the same time, if you look at all the air molecules in between where my mouth is located and where the listener's ear is located, no air particles are making that entire journey. They're only vibrating in place. And as they are vibrating, they are transferring energy. And through that energy, information is getting transferred in the form of an acoustic wave. So that's an example of information transfer through a wave phenomenon. Similarly, when we talk about information transfer through internet, okay, so there are many processes that is happening. Like if I'm typing out something, then the physical process of typing on keyboards, pushing those buttons, that is getting that mechanical energy of physically pushing those buttons is in, is resulting in small electrical impulses, which each of those buttons are sending in through the keyboard device into a digital processor, and those electrical impulses are finally getting converted into digital signals, which are in the binary language. And those digital signals, according to the binary language of ASCII code or whatever, they're interpreted as each of the letters, and that coded file is then getting stored in a hard disk, and then is getting transferred to your inbox or whatever. So that whole process of information going from one point to another It does not involve electrons or any particles like that going all the way from here to, let's say, San Francisco, where somebody might be reading the email. Nothing like that is happening. The information is getting encoded into such a phenomena which causes information to transfer from point to point just through vibrations of the individual molecules. Or in the case of optical fiber optic network, that information is getting encoded into signals which are electromagnetic in nature, just like light. Okay, and those waves propagating through the fiber optic cable is transferring the information. So any process, broadly speaking, which fits this description, that we are able to propagate energy or information or both without physically transporting particles from the source of the energy to the recipient of the energy. Okay, that is basically a wave phenomenon. Okay, now as we have seen through these examples, wave phenomena further categorized into situations like this one, or this one, which involve what we call mechanical waves. So in mechanical waves, what is happening? This kind of situation is happening. That there are physical particles of a physical medium which oscillate. But again, they oscillate, so they are in motion. But it doesn't mean that they are moving from the source to the recipient, or their motion is not causing the propagation of energy. I mean, their motion is not along the direction of propagation of energy. It's their oscillation that is transferring from particle to particle, and each particle has a fixed mean position. So by that transfer of the oscillation energy, the energy of the wave is getting propagated without the mean position of the particles ever moving. So those are mechanical waves. Okay. Whereas the examples like this that we have taken, light, visible light, radio waves, X-rays, microwaves, most of the processes involved in transfer of information by the internet, these all will involve electromagnetic waves, where basically it is electromagnetic oscillations are taking place through space. Instead of particles oscillating, okay, it is electromagnetic oscillations, which is why, as you know, electromagnetic waves do not require a physical medium. They propagate through space. So light propagates through space. X-rays propagate through space. Radio waves propagate through space, whereas sound waves do not. Okay. Because unlike a long-held belief in history that space consisted of matter called ether, it is now a scientific fact that there is no such thing, and space is actually vacuum. Okay, so that is why sound does not propagate through space. So this is just for your information, the broad description of the term waves. Now we come to the more specific term of mechanical waves. Yes, heat transfer also involves a wave phenomena. Okay, in both cases, like whether it is, we are talking about heat conduction, in which case it is the vibration of the molecules of a solid material which is causing heat energy, or basically kinetic energy of the vibration to transfer from point to point. So that is also a heat wave that is transferring through conduction. So in a sense, it's a mechanical wave. Or we are talking about radiation, which is all about electromagnetic waves or electromagnetic radiation. Or we are talking about convection. Now, convection is more like a particle phenomenon, because in convection, what happens that convection currents are set up. So sets of molecules which are at higher temperature will start moving faster because they have more energy, and they will physically displace from a warmer region of the liquid to a cooler region of the liquid, and with it they will carry that heat energy, that kinetic energy in the form of heat energy. So that convection currents, you could say, Ayush, is more an example of particle phenomena, whereas heat transfer by conduction or heat transfer by radiation is more like a phenomena related to waves. Okay, so hope that answers your question sufficiently. Now, coming to mechanical waves, you've already seen the definition of mechanical waves in a sense earlier. Okay. It is a process by which energy, mechanical energy, is propagated through a physical medium or a material medium via vibrations or oscillations of its particles. Okay. So it is a process of propagation of energy. And in this case, it is mechanical energy through a material or physical medium by oscillations of the medium particles, atoms or molecules as be the case. Okay. So the biggest two examples of this you can think of is sound, whether it is propagating through air, water, liquid, or through a solid. Sound can propagate through rocks and all that also. Okay. So that's one very important example of ocean waves, which are a surface phenomena. Okay. Or the example of waves on a stretched string. So that is example, any stringed instrument. All these are examples of mechanical waves. Now, based on this definition, we, as you sure know, we further classified into two categories, right? Longitudinal waves and transverse waves. So longitudinal mechanical waves are those where the medium particles oscillate along an axis which is perpendicular to the direction of energy propagation. Whereas this one is where medium particles oscillate along an axis which is parallel to, or which is along the direction of propagation instead of being perpendicular. Okay, so again, an example of this is ocean waves. I mean, by ocean waves, I'm covering that situation of ripples on any liquid surface also, okay, not just the ocean waves, but uh, vibrations of a string. So, for example, if you visualize a wave propagating along a string, so you see that the shape propagates like this. Okay. This is the propagation. But if you just put an ink mark on any point on the string, you will see that that ink mark is only going up and down. So this is the axis of propagation. Sorry, the oscillation axis. So any particle on the string, it only oscillates up and down like this, whereas the whole wave or the energy with it is propagating perpendicular to that. Okay. Whereas sound is the most common example of a longitudinal wave. So for example, if you visualize this kind of a situation, you have an air pipe or what is called a sound pipe or an organ pipe. You think in terms of musical instruments, wind pipes, or they are specifically called organ pipes. Now, if we create a disturbance at one end like this, like a tuning fork has been sounded, so it's going back and forth like this. So the sound wave as it propagates through this is the direction of propagation, but this is also the axis of oscillation. So it's not like the particles are propagating along with the energy of the wave. The particles are only oscillating back and forth. Their mean position is fixed, but the axis along which they are oscillating is along the propagation of energy axis or the propagation of the wave axis. Whereas in the case of transverse waves, it is perpendicular to the propagation axis. So that is the differentiation between transverse and longitudinal, or classification on the basis of this. So in this section, we'll be talking about mechanical waves, starting with transverse waves, using vibrations of a string as a physical model for studying the mathematical model of transverse mechanical waves. And the second chapter of this section will be longitudinal waves, which will be the physical model will be sound. And once again, we'll be discussing about sound propagating along a fixed axis. So basically one-dimensional sound waves. For that, the physical model will be sound waves propagating through a wind pipe, like the one I've drawn over here. Okay. So, I mean, more often in real life, what we see is sound propagating in three-dimensional space. Okay. But at our mathematical level, we'll be studying only one-dimensional sound waves. So sound waves propagating through wind pipes or organ pipes or whatever we call them. So the first chapter in this will be transverse mechanical waves. And in this also our study is going to be limited mathematically. Yes, Nikita, I'll scroll up just a minute. Okay. Mathematically, our study will be limited to one-dimensional transverse waves on a stretched string. This will be our physical model of studying this. Okay, so finish with this, Nikita.
Yes, sir. Done.
Okay. Now to develop the mathematical model, okay, we will use a sort of fixed convention that any vibrating string along which we are sending these waves or along which we are observing the propagation of waves, we will always think of that string as our x-axis. So we will designate our x-axis to be an infinitely long stretched string with one end at x equal to 0. So in that case, what happens is that the x coordinate at any point represents the x coordinate at any point represents the location of a particular medium particle. It is a particular point on the string is like a particular medium particle. So the x coordinate is like a address. Think of it like an address of a certain point in the medium. Okay. Whereas as a wave is propagating through it, I think of a pulse or something like this propagating through it. So as it is propagating, it will have at any point of time, it will have a displacement like this. So that displacement is along the y-axis. So as a wave propagates, any point x equal to x on the string has a transverse displacement y at any instant t equal to t. So this transverse y displacement, it has to become a function of x and t. So now we are going to deal with two-dimensional functions, or actually instead of two-dimensional, we say it is double variable function because they're not like function of x and y, it's function of x and t. Okay. So the transverse displacement is a bivariable function of x, which is position, and t, which is time. So any mathematical equation that we write to represent a wave will have to be of this form. First of all, it will have to express the transverse displacement as a bivariable function or a double variable function, so that it expresses for a particular point at x equal to x at a particular instant of time t equal to t, what is the transverse displacement. Okay. Now we will just discuss one more thing today before we wind up. So we will come back to waves again in the next lecture. We'll just talk about a little bit of graphs, okay, transformations, and something very interesting, moving graphs. So let me just explain this with an example. Okay. If I have drawn, oops, coordinate frame like this, and in this, I first of all I plot the function y is equal to x square. Suppose, okay, just as an example. No particular reason why I picked up this particular graph. So this looks like this, okay. But if I now transform it to y is equal to x minus 1 whole square, what happens? This whole graph shifts towards the right by 1 unit. It's a transformation by 1 unit like this. Okay. Similarly, if I want to transform it in this direction, I should make it y is equal to x. It's a plus 1 whole square. Okay. This is something I'm sure you are aware of, that any graph can be shifted. So in general, the graph of any function, whatever that function be, whatever the shape of that function, it can be shifted horizontally like this by transforming, replacing x with x minus d, gives it a shift like this. But now in this, what if I make it where d is v into t, where v is a constant and t is time. So what will happen in that case is that this will be a constantly shifting graph. So for example, on the one hand, I have the graph of, let's say, e raised power minus x square. And on the other hand, I have a graph of e raised power minus of x minus 2t whole square. Now let's compare these two and understand what's happening here. So you see, one is a fixed graph and the other is a moving graph, which moves at a constant rate. So what will the graph of e raised power minus x square look like? You tell me the shape of this graph, what it should be like. Anyone? You've done a bit of graphs in calculus and all that before.
Yes, sir.
It look like a pulse kind of shape. Na? It's exponentially decaying on either side. It has a global or local maximum of 1 at x equal to 0. Okay. Now compare this with how this graph will be looking. So if I plot this graph at t equal to 0, obviously it's the same. So this one I can see, for example, y at t equal to 0 is e raised power minus x square. But what about y at t equal to 1? It becomes e raised power minus of x minus 2 whole square. Then what about y at t equal to 2? It becomes e raised power minus of x minus 4 whole square. You can see it becomes a traveling graph. It's this very interesting thing. It's like this pulse, which is traveling at a constant rate. This is at t equal to 0. But now, if I observe the same function after a time of 1 second, I'll see that it's like this pulse is shifted. And during that 1 second also it's constantly shifting. Then at t equal to 2, it's again shifted. So this should be 2. So every 1 second it is shifting by 2 units. So in general, at some time t, this pulse would have shifted like this, where this value will have become 2t at time t. Okay. So this is an example of a, so if we transform a function y is equal to fx into a function f of x minus bt, we change the argument of the function to this. It becomes a traveling shape. The graph becomes a traveling shape. And not only it's traveling at a uniform speed of v along the positive x-axis. So it's traveling along positive x-axis at uniform. Similarly, if I transform this to f of x plus vt, now this will be traveling along the negative x direction. At again the uniform. Okay, so this is something that we'll use in the mathematical model, because you can just imagine this example only. Just imagine this is like a pulse, that a single jerk that you have created on that string that we were talking about earlier at the point x equal to 0. So now the elasticity of the string, it will carry that jerk along the positive x-axis. So this is how it will look. At various instants of time, it will look like that peak is shifting. So if we have to represent it mathematically, we'll have to represent it with some appropriate function like this, where the argument of the function, instead of being x, it will be a time varying quantity. So it will be like x minus vt if it's traveling along the positive x direction at a constant speed t. Okay. So this is going to be our first tool in developing the mathematical model of one-dimensional transverse waves, that is based on a string, which we're discussing earlier. Okay. So we'll conclude today's session here, but you can get started with some reading from Resnick Halliday or even H.C. Verma if you want to have a very short description of it. And that will definitely help in the coming few lectures. It's a very conceptual topic, wave mechanics. Okay. And if you're clear with the concepts and derivations, you will find the problems interesting and fun to do. And accordingly, you can score very well in JEE. Whereas if you try to just have a formula based rote learning kind of approach, then you might get confused sometimes with the more tricky problems. So better to have a conceptual approach from the beginning. And if your approach is conceptual enough, the problem solving is not difficult. So unlike mechanics, you're not likely to get stuck with questions and at the exam level make a lot of mistakes and all that. That's unlikely to happen if your concepts are clear. Anyhow, so that's it for today's session. People, wish you all the best. Have a nice day.
Thank you, sir.